More encryption techniques. AES, of course, is the official government recommended symmetric encryption, so this is one we should all be using unless you need public key encryption. And so AES, this is the simplest mode that has 16-byte key. Let me bring it up here. I had to do this install of this library, PyAES. PyCryptoDome, I think, is a bigger, more general library, more recommended these days, but this one still works, so it's good enough. And so if I look at aes.py, all right, so the key has to be 16 bytes long, and the plain text is also 16 byte long in this case. If it's longer, then you have to pad it to make a multiple of Cryptodome is an acronym. Yes, PyCryptoDome, that's right. PyCryptoDome is the really good one. I learned that from a great online game, Crypto Hack, which is fantastic. Anyway, so now you can just encrypt it. You import PyAES, and now you define AES to be this mode of. This creates an AES object, which is going to perform the AES operation using ECB, which is the simplest thing called textbook encryption, which is not recommended because it has severe weaknesses. But you can encrypt it here. You encrypt the plain text, and you can print it out. And when you encrypt something, of course, even if it is readable ASCII, the encrypted stuff is no longer readable ASCII. The bits are all scrambled, so you have to print it in hex if you want to see it. And so if you run that, you get this hex stuff here. And let me show you the weakness of this mode while I'm here. If I make my plain text longer, by just adding the same 16 bytes again, and the same 16 bytes again, and now I run that, it must be 16 bytes. Oh, okay. Then I guess it's not something I can demonstrate easily live, but the point is there is no randomness here. This is like Microsoft password hashes. If I have a plain text of this 16-letter message and that key, I'm always going to get that same result. So if there's repeated blocks in the input, they'll be repeated in the output in this electronic codebook mode, and that's why there's that famous demonstration where you encrypt something this way, and it will not hide the contents of an image if you have a simple bitmap, because there are blocks of same color, and they'll still turn into blocks of same color. So that's why this electronic codebook mode is no longer recommended for almost any purpose. But it is an option, and you can use it here. So there's just some challenges here where you have various things to encrypt and decrypt. And here you have a key contains only one of two letters and is 16 bytes long, so you can brute force all of those. And on you go. Notice that it has the PBKDF2 password-based key derivation function, which is the same thing essentially that Linux uses to encrypt password hashes. So you add a salt and you do 1,000 rounds of SHA-256. That's how you turn a password into a key. And then there's counter mode, which is much better, where you have just a number that counts up, and you append that number to each string of plain text before encrypting it. So if two blocks are the same, they're no longer the same. That's one of the more secure methods. The most recommended these days is GCM, which is Galois counter mode. And again, it's French, so I think I'm pronouncing it wrong. But anyway, there's some AES challenges. And the next thing is the Rho method, which is very interesting. If you consider hash something, and then hash the hash, and hash the hash, and hash the hash, which, by the way, is how you make Bitcoin private keys from a memory wallet, and many other operations, then what will happen is you cache something, you hash it again, making H2, you hash it again, making H3. What will happen is eventually you'll get some hash operation that repeats one of your previous hashes. So eventually you will have a repeat, and then you will just go around this circle forever. Because when you hash this one again, you'll get whatever you got last time, and so on. Just like I was saying about Microsoft password hashes, if there's no randomness involved, then if you come back and put in the same input again, you'll get the same output. So this resembles the Greek letter rho, and the question is, how long would it take for things to repeat? And the answer is, it's a lot less than you'd think. You do not have to explore all possible hash values for it to repeat, more like the square root of all possible hash values. So here I can calculate an Md5 hash. We've done this sort of thing before. If I run Python 3, I import the hash library, and here I'm going to encode the string ASCII, or A. I'm going to take A is my input, encode it in ASCII, and then do the hex digest. So there's the MD5 of A, and you can check it with an online generator. It's 0cc1, so it works. So now what I'm going to do to make short hashes, just to play with, is I'm just going to truncate it. This is a string, and I can just keep the last 2 bytes of the string by adding a bracket -2 : at the end. So if I do this, I don't really need to import it again, but I put it there in case. Right, I got to kit the I though, all right. I put it there in case a student would get halfway through the project and then start again. All right, so now I get just the last 2 characters here, 61. So I've now made a very simple hash function that gives me just a 1-byte output so I can play with it. So now we can iterate it. You can do whole programs right here in the interactive terminal if you like, including loops and indentation. So I import hashlib, I start with the character A, now I'm going to calculate 50 iterated hashes. So H is the hash, and that's going to be the whole thing, the MD5 of the ASCII encoded characters turned into a hex string, and then I take only the right 2 characters. And then I'm just going to print it here. And if I don't want everything to appear on a new line, in Python 3 you can put an end character here, and it will put that at the end instead of a carriage return line feed. So I'm going to separate them by spaces so that more of them will fit on a line. So if you make a loop in immediate mode, I indented it by 2 spaces, indented it by 2 spaces, so now I press enter, and Python 3 does not know whether I'm going to have another enter in the loop, so I press enter again, and that will end the loop and run it. And here we go, 6191. The 61 we saw before is the first hash. Then when you hash this, you get other numbers that are essentially random. So if I look down here, here I see a D7, and here I see another D7. So I have made enough of them to make the loop. So if I just change the width of my screen, I should be able to line up. Here's the D7, and where's the other D7? Looks like it's not taking that resizing as well as it should. Might have to put it in a text editor. Let me just run it again. All right, I got to go all the way back to here. Okay, there's the D7, and there's the other D7, so I'm almost skinny enough. In fact, you can see it. Okay, I want to go back 1, 2, 3 characters. Okay, now it's 1, 2, 3, 4, 5. Okay, one more, I think. T7. I may not be able to do this live. There. Anyway, I was able to get the 1E's to line up. Here is 1E, and there's the next one. So I need it a little bit wider. Let's just run this one. All right, anyway, I managed to line it up here on my other terminal that worked better. And you can see it goes for a while hunting and then it finds the loop. So you can try this various ways. There are various ways to find loops here, even up to a 32-bit hash, you'll see. And that's the essence of the Rho method, how you find hash collisions, and this determines cryptographic limits for hash functions. This is why, for example, SHA-1 had to be 160 bits long, because they wanted 80 bits of security. And so if you have a hash function 160 bits long, you only have to calculate 2 to the 80 hashes before you'll find a collision for this reason. And it turned out that that was not true for SHA-1, which is why SHA-1 has been deprecated, and now we've moved to SHA-2 and SHA-3.